Hello students, welcome to section 8.7 part 2. We had technical difficulties on the last recording, so I'm going to give this a try again. Occasionally it is necessary to apply L'Hopital's rule more than once to remove an indeterminate form, as shown in example 3. So example 3, evaluate the limit as x approaches negative infinity of x squared over e to the negative x. We'll first try direct substitution. If you plug in negative infinity into the numerator for x and the denominator for x, you do in fact end up getting infinity over infinity. So we start the process as we've done in the past with the limit of the original problem just being rewritten. And by L'Hopital's rule, the derivative ddx of the numerator and the derivative ddx of the denominator lends itself to, in the next step, 2x over negative e to the negative x. We take that limit, and as it turns out again by direct substitution, 2 times negative infinity over negative infinity e to the negative infinity, or negative e to the positive infinity, excuse me, we end up with negative infinity over negative infinity. So we can apply L'Hopital's rule again. We do that. So by L'Hopital's rule, you can see that in the next step, ddx of 2x, ddx of negative e to the negative x, which in turn lends itself nicely to a derivative of 2 over a derivative of e to the negative x. Plugging in negative infinity into the denominator for x leads to infinity. 2 divided by infinity, of course, is 0. So the answer to this problem is just 0. Other forms that we're going to observe: 0 times infinity, 1 to the infinity, infinity to the 0, 0 to the 0, and infinity minus infinity. Examples include, for the sake of something that we could easily simplify by just dividing x over x. Of course, the limit there would be 1. But if you plugged in 0, it's indeterminate, right? 1 divided by 0, for example. And then the next limit, simply again, I would argue, easily just divide by x to get a limit of 2. But plugging in 0 again leads to something that is undefined or indeterminate. The other two examples are similar. If you were to apply L'Hopital's rule, this one in particular ends up being a limit of 0, while this one ends up being infinity. Because each limit is different, it is clear that the form 0 times infinity is indeterminate in the sense that it does not determine the value or even the existence of the limit. The remaining examples in this section show methods for evaluating these forms. Basically, you attempt to convert each of these forms to 0 over 0 or infinity over infinity so that L'Hopital's rule can be applied. And speaking of 0 over 0, this first example, but also the second example, would lend itself to that situation. So those are good examples of things to come. So example 4, the indeterminate form 0 times infinity. So we have a limit as x approaches infinity of e to the negative x square root of x. If you rewrite the problem such that e to the negative x is in the denominator is e to the positive x, and using direct substitution in turn, you plug in infinity here and infinity there, and you get infinity over infinity. And that, of course, is one of the two forms that we're attempting to convert to for the most part. However, if you leave the problem as is, leaving again, just as you see e to the negative x times root x, plugging in infinity here and here, you end up with 0 times infinity. Okay, so this particular type of indeterminate form, in the sense that it doesn't determine, like I said earlier, the value or even the existence of the limit, well, we need to still approach this using L'Hopital's with this form in mind. All right, so let's continue. So as I kind of stressed earlier, we can rewrite such that it looks like this: root x over e root x, or e to the x, pardon. The limit as x approaches infinity, ddx of x to the half, another version, of course, of the square root of x, as we know, over ddx of e to the x. The derivative of x to the half is 1 over 2x to the half, and the derivative, of course, of e to the x is just e to the x. We can rewrite this. Dividing by e to the x is the same as multiplying by its reciprocal, and therefore I can rewrite this as such: 1 over 2 root x e to the x. Now if you plug in infinity here as well as there, you've got a full denominator there technically of infinity, so 1 over infinity in simple terms, of course, is just 0. Let's move on. When rewriting a limit, in one of the forms 0 over 0 or infinity over infinity does not seem to work, try the other form. For instance, in example form, as we kind of wrote, but in a different way here, they're showing leaving e to the negative x in the numerator, but bumping the square root of x down to the denominator. That would have been an equally good approach. And still, using L'Hopital's rule, you would have seen this particular fraction take shape. Different fraction, but still applicable in the sense that you get what you want as far as a limit. And yes, the indeterminate form 0 over 0 is another version that we're shooting for. The indeterminate forms 1 to the infinity, infinity to the 0, and 0 to the 0 arise from limits of functions that have variable bases and variable exponents. When you previously encountered this type of function, you used logarithmic differentiation to find the derivative. You can use a similar procedure when taking limits, as shown in the next example. So example 5, the indeterminate form 1 to the infinity power. Evaluate the limit as x approaches infinity of 1 plus 1 over x to the x power. Now this may look familiar to you. You did actually see this particular expression in Algebra 2, but also in pre-calc. And before I speak about what that entails or what it did kind of play out to be, let's do the problem and we'll kind of go back to that idea. First and foremost, if you use direct substitution to see what kind of form you're dealing with, if you plug in infinity for x, in these two instances, you then end up with 1 to the infinity power. And that is, of course, an indeterminate form of which, well, we're going to have to use L'Hopital's rule to justify, but also some other approaches here, as you'll see. Another thing that you're going to need to do here is you're going to have to call the entire expression y, because as it says up above, we use in the past logarithmic differentiation to find the derivative. We're going to do that as well here. Okay, so let's take a look. So now this entire problem is now written as y equals the limit as x approaches infinity of 1 plus 1 over x to the x power. We can take the natural log of both sides. The reason we want to do that is so that we can rewrite the problem after, of course, L'Hopital is applied. Rewrite the problem in a manner in which we can express it as, well, an actual value. We'll see that here unfold shortly. Okay, so because the natural log is continuous, I'm able to interchange the limit and the natural log. So I'm actually taking the limit of the natural log now of that same expression. The next step that I apply is moving the x out in front thanks to the power rule that you learned for natural logs and logs in Algebra 2 and pre-calc. So our next expression looks like this. If we do direct substitution, plugging in infinity here as well as there, we get infinity times 0. And then we continue on by rewriting the expression. So we have yet to use L'Hopital's rule. I'm going to take x and rewrite it as such. So it's, instead of x times this, it's that quantity divided by the reciprocal of x, so 1 over x in the denominator. Direct substitution, yet again, in this particular case, plugging in infinity nicely enough, plug in infinity here as well as there, lends itself to 0 divided by 0. Perfect. This is exactly what we want in order to particularly apply L'Hopital's rule the right way. So ddx of the numerator, ddx of the denominator, again, as L'Hopital's rule speaks to. The numerator in particular ends up being negative 1 over x squared over 1 plus 1 over x. And then the denominator, the derivative of 1 over x, in other words, is simply negative 1 over x squared. The nice thing that does unfold here is that these two fractions are the same, so we can divide them out and get 1. So now we have 1 over 1 plus 1 over x, as you see there in the next step. Plugging in infinity is quite nice. I did that, and this entire quantity noting here is just simply 0. Therefore, 1 divided by 1 is equal to 1. If you remember the beginning of the problem, when I took the natural log of both sides, I still have natural log of y on the left side. I just got 1 on the right side. So if I took this equation and rewrote it in exponential form, the base is e. So e to the first power equals y. So this hopefully looks familiar to you. Y equals e. The limit is simply e. If you remember back in Algebra 2 and pre-calc, this expression and the limit of that expression more particularly, even though you didn't know what a limit was back then, it is something that you did look at to decipher how e kind of takes shape. It's a proof, if you will. L'Hopital's rule can also be applied to one-sided limits as demonstrated in examples 6 and 7. Now we're going to finish with example 6. Example 7 ends up being something that you can kind of view on your own and research from what the book depicts. Example 6. So the indeterminate form of 0 to the 0 power, evaluate the limit as x approaches 0 from the right of sine of x to the x. Yet again, I'm going to call this entire quantity y. If you do direct substitution, you get 0 to the 0 power to kind of kick the problem off. All right, so again, that will prompt you, once you again say that this entire expression is equal to y, that is going to prompt you to take the natural log of both sides. So the problem again is rewritten as y equals the limit of as x approaches 0 from the right of sine x to the x, then taking the natural log of both sides. Again, continuity of natural log speaks to you being able to kind of switch or interchange the natural log with the limit. So we're taking now the limit as x approaches 0 from the right of the natural log of sine of x to the x. The power rule allows us to move the x out in front, and then we're going to use direct substitution again, wherein if you plug in 0 here and here, you get 0 times negative infinity, which technically is not what we're looking for. To use L'Hopital's rule, we want either 0 over 0 or infinity over infinity, or a version thereof, like negative infinity over infinity, as we're about to see here in the next step. Yet again, I can rewrite x as opposed to multiplying it by natural log sine of x, rewriting it where it's in the denominator of a fraction. So natural log of sine of x over 1 over x. Now by direct substitution, plugging in 0 both for the numerator and the denominator and in x, we get negative infinity over infinity. That is indeterminate, of course, still, but we can now approach it using L'Hopital's specifically. ddx of the numerator, ddx of the denominator. The derivative of natural log of sine x is cosine x over sine x. The derivative of 1 over x is negative 1 over x squared. Cosine over sine is cotangent. The same denominator as you see continues on. Now we can rewrite the problem in the next step as such. We can apply using, well, first rewriting this first, because cotangent is 1 over tangent, I can rewrite it like so, and I can also take negative 1 over x squared multiplying by its reciprocal, so this is the fraction that takes shape. Before I apply any more L'Hopital's rule, you can see I plugged in 0 here and here, so we've got an indeterminate form technically here. We still can't find the limit. So yet again, by L'Hopital's rule, the second L'Hopital's rule, again, if we take the derivative of negative x squared, we get negative 2x. Take the derivative of tangent of x, we get secant squared x. Then if you plug in 0 here, as well as there, you do in fact get a nice value, a limit of 0. Again, remembering from the beginning when we changed the problem into y and also took the natural log of both sides, natural log of y on the left still now is equal to what? 0. The base is e, so e to the 0, which of course is 1, and that equals now y. So y equals 1 as your final limit. Example 7, this particular question, I did ask kids to finish individually in the past. The full solution is right here for you to take a look at. It's a very interesting case that expounds on what we've been discussing. Infinity minus infinity is the indeterminate form that we're taking a look at and applying in context. So if you evaluate the limit as x approaches 1 from the right of this expression, you will end up, using L'Hopital's rule again, of course, you will end up with a nice limit.